In this video, the learning goal is I can identify the knowns and unknowns for each section of constant acceleration. So, from our lab the other day, we talked about Galileo and his experiment. So he dropped two balls from the Leaning Tower of Pisa and found that both of these cannonballs hit the ground at the same time. And then we did a lab in which a ball rolls down a ramp. And we came up with an equation similar to this bottom one. So the initial speed that we dropped our ball with, v naught, is our initial speed. If we dropped the ball, meaning we kept the ball, it was at rest, initially the initial speed was 0. So 0 times any number is just 0. So the equation that we came up with in the auditorium was something similar to this form. So now we're going to find out how to use this equation. So let's look at our question number 2, the situation. When Maggie applies the brakes of her car, the car slows uniformly at 15 meters per second to 0 meters per second in 2.5 seconds. How many meters before a stop sign must she apply the brakes in order to stop at the sign? So this is a complicated question, but what we can do in physics is we take a complicated problem, and we break it down into things that we know, things that we don't know, and then we try to apply equations, mathematical equations, to solve these problems. So let's figure out what we know first. When Maggie applies the brakes of her car, the car slows uniformly from 15 meters per second to 0 meters per second in 2.5 seconds. So if she's going from 15 to 0, I can say my initial speed, this is initial speed right here, the symbol, is 15 meters per second. My final speed, think F for final, is 0 meters per second. And the time that it takes to go from 15 to 0 is 2.5 seconds. So these are 3 things that I know. The question is asking how many meters before a stop sign must she apply her brakes in order to stop at the sign. If we want to know how many meters, this is a distance. How many meters? What we're trying to find is how many meters. That's our unknown. Now let's just quickly remind you what all these symbols mean. A is acceleration. Vf is final velocity. Vi is initial velocity. T is time. And there's one more, and that's x, which is your distance, your displacement. Okay, so with any one of these equations, look, if I know three of the variables, I can always find the fourth. So we got to pick an equation that has all 4 of these variables in it. So let's look. Looks like the second one has all 4. So let's see. It has our unknown there, our initial velocity, our final velocity, and our time. So the equation that we could use to solve this is this one. All that's left to do to solve this problem is plug in our numbers for v initial, v final, and time, and we get an answer for the displacement. Let's look at one more question. A flower pot falls from a windowsill 25 meters above the sidewalk. How fast is a flower pot moving when it strikes the ground? So we don't have a lot of numbers here. We've got to really think about what's happening. A flower pot falls from a windowsill. So if you can picture, here's my windowsill, here's my flower pot. Here I've got my flower in it. and it just falls over the edge and it starts moving down. So if we think about this, the initial speed of the flower pot, right when it starts to go over the edge, its initial speed is 0. It's not moving at the beginning, right? A different scenario where it would not be 0 is if you took the flower pot and you threw it. You threw it straight down with some initial speed. But in this scenario, no, it just falls, meaning its initial speed is going to be 0. Okay, falls from a windowsill 25 meters above the sidewalk. So if I start here and I fall down in this direction, okay, I'm going to say if this is my positive y direction, that means that my fall, you can use the letters x or y, because now we're talking about the y direction. In the y direction, my fall is 25 meters. So what's with this negative? Well, if I were to throw a flower pot up to a friend who's on top of a building, so I'm throwing this flower pot up this way, and if I were to throw it up 25 meters, well then this would be a plus 25. But since it's falling down, and I'm saying, well, this is usually what we define as the positive y direction, right? Positive y direction, positive x direction. So since I'm defining up as the positive y direction, if a flower pot falls down, that's going to be negative 25 meters. There's one more piece of information we know, and that is that falling objects on the surface or near the surface of Earth will always have an acceleration of negative 9.8 meters per second squared if we ignore air resistance. So ignoring air resistance meaning my acceleration is going to be down. This makes sense that my acceleration is down. If I drop an object, my dots get farther and farther apart, so my acceleration must be down. All right, those are our 3 knowns. Our unknown, how fast is the flower pot moving when it strikes the ground? Well, we want to know its final velocity right before it strikes the ground. Okay. Now remember, we can only look at these equations in sections of constant acceleration, meaning the beginning it's at rest, my acceleration is 0. Then it starts accelerating down, and then at the end it's at rest as well. So I need to look into the section from right once it starts to fall to right before it hits the ground. So my final velocity, I'm not going to say my final velocity is 0 because that's looking at a different section of the acceleration. I need to find the final velocity right there, the moment before it hits the ground. So which equation are we going to use? Let's look at this. V initial, V final, y, and acceleration. V initial, V final, y, or in this case, the equation has x, but now we're looking in the y direction, and my acceleration. You can write delta x, or in this case, we can write delta y. The second says, how much time does it take? Okay, this one's easy. How much time? That's what are known. On the sidewalk below before to move out of the way. Okay. So let's look at this. How much time? Now we want an equation that has 1, 2, 3, and 4. Now, could we have chosen this one as a variable that we know? Well, yeah, we're going to find some answer for this, right? Just say we were to find some answer. Let's make up a number. 10 meters per second. We're just making up a number. That's not actually true. Okay, I could have used that 10 meters per second and any one of these two to find my time. But it's always better to go with the variables that we're absolutely sure about, not the one that we calculated in case we made a mistake calculating it. So 1, 2, 3, V initial, Y, A, and T. V initial, Y, A, and T. So it's going to be this equation. delta y is equal to VO delta t plus 1/2 a delta t squared. And that's all there is to it. So remember, these equations, they only work for sections of constant acceleration, right? So right when this flower pot leaves this windowsill to right before it hits the ground. Once it hits the ground and my velocity is 0, these equations will not work. We can't mix two sections of acceleration. Cool. I hope this helped you identify knowns and unknowns for each section of constant acceleration.